So in this lesson, we're going to talk about the intersection of two planes in the 3D coordinate system. Let's just go ahead with an example problem. So let's say plane 1 was x minus 5y plus 3z equals 2. The second plane is, 2x minus 6y minus 4z. Actually, no, minus 3z equals 3. So we want the intersection between the two planes. So the first thing we want to do is there an intersection? We want to figure out, is there an intersection? If there isn't an intersection, then we don't have to waste our time on this problem. We just answer no and we move on to the next question. So is there an intersection? Well, essentially what we want to do to find an intersection is actually just to solve the system of equations over here, right? Because if we solve this and we figure out, so x, y, z are essentially coordinates. If we figure out that there are x, y, z's, that there are coordinates that fit this description, that solve the system of equations, then this coordinate, the point with this coordinate x, y, z is an intersection of the two planes. If we can't solve the system of equations here, then the two planes don't have an intersection. So how do we solve this? Well, we do this, so obviously we can't actually solve this because there are 3 variables and 2 equations. But what we can do is we can try to use our usual method, which is eliminating variables. Now, if I call this expression 1 and equation 1 and equation 2, equation 1 plus equation 2 gives us, so on the left hand side we have x plus 2x, which is 3x, negative 5y plus negative 6y minus 11y, 3z minus 3z, which is 0, and then we have 2 plus 3, which is 5. So that's actually so we get this new equation over here, which we'll call equation number 3. So how does this actually help though? Because now we have one equation which we can't solve because it has 2 variables. So that's not really helping, is it? But the key here is that if this equation has a solution, then there might be an intersection between the two planes. If this equation does not have a solution, then there is no intersection between the two planes. So is there a solution to this equation? Well, it does seem like it, because I don't know, maybe you can for example, when x is equal to 5, then this is 15, right? 15 minus 10 is 5. So y is going to be equal to 10 over 11. This actually is a solution. I trust that you can figure out that there are many more solutions and that there are infinite many solutions to this equation. Now, what does this mean then? Having infinite many solutions instead of one set of x, y, z. Well, this means that our intersections align. So let me just write that down. Infinite many solutions. Actually, I'll type it. So infinite many solutions means the intersection is a line, because the line actually extends in 2 directions forever, right? So there's infinite many points on that line, meaning there's infinite many x, y, z solutions for this equation. Okay, so we know that the intersection is actually a line. So that's just great. That's a bit of progress, right? So how do you find the intersection? Essentially, what we want to do is find the equation of this line. So we want to find the equation of this line. Okay, so we're gonna first start off by, representing. So we're gonna try to use parametric equations, because the only way to represent lines in 3D coordinate systems is by using parametric equations. So what's the parameter? I'll just make the parameter be z. So the parameter is z. Okay, or let's just make the parameter t and z equals t. Now what about x and y? So here, from 3, we derive that. So from equation 3, we derive that 3x minus alpha and y equals 5, right? So basically what we get is that 3x is equal to 11y plus 5. And then x is going to be 11 over 3y plus 5 over 3. That's x. So we represented x in terms of y. Now we only want to represent z and y in terms of z, and then we can represent x and y using parameters, and problem solved. So we can plug this in. So this is 4. We'll plug this in. 4 into 1. So if we plug 4 into 1, x is actually 11 over 3y plus 5 over 3 minus 5y plus 3z. So plus 3z, or z is t, right? So that's our parameter, equal to 2. So 11 over 3 minus 5y is 11 over 3 minus 15 over 3y, which is negative 4 over 3y. And then if we move the other stuff to the right hand side, 2 minus 5 over 3 is 1 over 3, and we have minus 3t. So if we multiply both sides by negative 3 over 4, so negative 3 over 4 will give us, so we multiply this by negative 3 over 4. Then this will give us, so firstly, for this 1 over 3 times negative 3 over 4, we get negative 1 over 4. For this negative 3t, we have plus 9 over 4t. So that's actually how our parametric representation for y. So let me just box that. Right, and this is our parametric representation for z. So if we plug this in, if we plug this number 5 in, so if we plug number 5 into number 4, then what we get is, so x is equals to 11 over 3 times this stuff. So if we expand that, 11 over 3 times negative 1 over 4 is negative 11 over 12. And then we add that to 11 over 3 times 9 over 4t, which is 99, or actually no, we can simplify the fraction. So that actually gives us 33 over 4t. So, and then we add that to 5 over 3. So we simplify that, x is equal to 33 over 4t. Plus, so 5 over 3 is equal to 20 over 12, right? 20 over 12 minus 11 over 12 is 9 over 12. 9 over 12, if we divide the numerator and denominator by 3, is 3 over 4. So that's just our answer. So that's our answer for x. So we represented x, y, and z using parametric equations. So we represented our line in the 3D coordinate system. So problem solved. So that's just our answer to this problem. The 3 boxed equations. So we put them together and we get the parametric representation of a line. So thanks for watching. Bye.